everyone. This is Beth Conway with the Water Environment Federation. I want to welcome each of you to the Nutrient Removal and Wet Weather Flow Management e-Showcase. Before we begin, I would like to quickly review a few logistics. During this webcast, while you cannot speak directly to the presenters, you will have an opportunity to submit questions by typing your specific question into the GoToWebinar pane that appears on the right-hand side of your computer screen. I will be accumulating questions and will direct them to the presenters at the end. The PDF PowerPoint presentations are now available for downloading at WEF's website and are currently available in the Handouts pane of the GoToWebinar panel. This link was included in the GoToWebinar reminder email sent an hour before the webcast and will be included in the follow-up email sent within 48 hours after the webcast has ended. We will be recording this e-Showcase. The recording link will be available on the webcast website within 48 hours after the webcast has ended. PDH credits are not available for this event. Please note that today's event is an e-Showcase and does not necessarily reflect the views of the Water Environment Federation. If you have any additional questions after the webcast has ended, please email webcast@wef.org. Today's speakers are Tracy Mayer and Brian Tierney. Tracy and Brian are technical sales engineers at Evoqua. Tracy and Brian, I'll hand it over to you.
Thank you for that introduction, Beth, and thanks for all the attendees for logging in today for our webinar. As Beth mentioned, we're here to talk to you about nutrient removal and wet weather flow management in regards to SPR technology. So the issue affecting plants all over the country is increasing wet weather flows and decreasing nutrient limits or more stringent permits. And this figure here shows maps the overall flow change measured by the USGS over the past 100 years. The Midwest in particular has seen dramatic increases, as shown by these large blue triangles. These changes can be detrimental to plants not designed for high wet weather flows, especially the thousands of SPRs nationwide. All right, got advanced. All right, so what is an SPR? An SPR performs the same treatment steps you're familiar with in a conventional system. Influent enters the system. The system that's selected for treatment treats the wastewater. Treated effluent leaves the system, and waste sludge is removed. With a conventional system, you have distinct treatment spaces or separate tanks or zones for each step of the process. In this example, we've got an anoxic step, followed by aerobic treatment, followed by clarification. And that tank volume for each step of the process is fixed until it's modified during a future project for lower limits or increased flows. Now, in an SPR system, you can remove the sludge recycle and the internal recycle because the biomass stays put in one tank, designed to provide anoxic treatment, aerobic treatment, as well as your clarification, all in the same basin. Same mass balance applies, influent enters, wastewater is treated in the system, treated effluent leaves the system, and sludge is wasted out. The SPR performs these treatment steps at different times during the cycle. And this provides for a lot of flexibility and allows the plant to modify cycle times to achieve different levels of treatment in the same volume. Over the past 35 years, JetTech has designed and installed over 700 SPR installations. We've made continuous improvements along the way. Notably in '85, developed the vac flush cleaning system, which allows the operators to very easily clean out any plugged jets, as well as the influent distribution, sludge collection manifold systems, and flow proportional controls. In 2005, came out with the OmniPack SPR Field Direct system, which allows for easy installation. And most recently, we launched our OmniFlow SPR Max system in 2018, which Tracy will dig into shortly. Traditional true batch SPR systems typically have a minimum of 2 SPR basins, or 1 SPR basin and 1 EQ basin, so the system can always accept influent flows. A single cycle for each reactor consists of 5 discrete periods: fill, react, settle, decant, and idle. And we've got a video that can illustrate these 5 steps. So in the first step, fill, the influent valve opens, allowing the basin to fill. Followed by step 2, react, where we cycle the air on and off to hit a DO set point. Followed by step 3, settle, or the clarification stage, where the blowers and pumps are turned off for quiescent settling. Step 4, decant, allowing the clear treated supernatant to be decanted out of the system. And that's followed by step 5, where we're in idle, waiting for flow to come back to that basin, and we're able to waste out sludge during that time. Video is pretty quick, so I'm going to run through it one more time. Again, step 1, open the valve, fill the basin. Typically no air during this point of the process, so you get some anoxic treatment. Step 2, turn the air on and off. Step 3 is our clarification stage, getting the sludge to settle down so we get a clear supernatant layer that we can decant out in step 4. So as I mentioned, only 1 basin fills at a time for excellent batch kinetics, allowing for complete biological nutrient removal. We can get TNs less than 5 milligrams per liter and TPs less than 1 milligram per liter. The true batch system allows you to avoid short circuiting, which can degrade effluent characteristics. And you also get improved settling with the anoxic fill selector process, which can minimize sludge bulking and control filamentous growth. And now I'll turn it over to Tracy to discuss the problem true batch SPRs suffer and our solution.
Thanks, Brian. Brian highlighted the benefits of a true batch SPR system, including its flexibility. The main drawback with SPRs is wet weather flow handling. Because with a true batch process, because of the nature of a true batch process, all of the influent is directed to one of the SPR tanks at any time. Since most SPR systems operate in 2 or more tanks in parallel, only a fraction of the total SPR volume is available to receive flow at any one time. So if there's 2 tanks working together, only 50% of that volume is receiving flow at any one time. So that results in a very high hydraulic loading rate for any SPR system. As you can imagine, that gets worse the more tanks you have. If you have a 4-tank system, you're directing all of that flow to only 25% of your tank area. This can disrupt the sludge blanket, as shown in this picture here, and it results in poor effluent quality and a loss of biomass, which is especially important under those high flow conditions where you have diluted influent coming in. You really need to keep all of the biomass that you can in your SPR tank. Traditionally, SPRs have handled wet weather flow by designing for additional tank volume in one of two ways. Either you can have influent equalization tanks to divert those, to help shave off those peaks, or you can have additional freeboard in the SPR tanks. And that's just creating extra volume so that you can have maybe additional batch volume in each tank. But under the majority of that time, that freeboard is unused and kind of creates excessive tank volume. In order to keep up with the hydraulics coming in, traditionally those SPR cycles that Brian went through are compressed because you're filling more quickly and hitting top water level more quickly. You really have to compress those 5 steps that Brian was talking about. Eventually, you'll have to compress those cycles so far that you'll have to achieve some of those steps simultaneously, such as decanting while you're filling. And so it's really important to have a good tank design in order to try and limit that short circuiting that Brian was talking about. Evoqua's traditional approach for this in SPRs does include compressing the cycles in order to keep up with the increased hydraulics, but it does not require additional tank volume in the form of influent equalization or freeboard. Our new approach still includes compressing cycles to keep up with the faster fill rates. In addition, we've designed the controls to recognize when wet weather flow is happening, and it will automatically open influent valves to all available SPR tanks. This maximizes the buffering capacity by using all available SPR volume rather than forcing that flow through one tank. So rather than sending that peak flow rate to 25% of your tank volume with, if you're filling one tank of a 4-tank system, with this new OmniFlow Max control strategy, you can actually fill 100% of the tank volume that you have, so that it really results in a better hydraulic design. With this approach, you still get all of the benefits that Brian talked about, the flexibility and the biological nutrient removal, because you're still maintaining that true batch process under average flows. During wet weather flows, the control system automatically adjusts to open all of the influent valves. Once the flows reduce back to typical flows, the controls will revert back to that true batch mode that Brian was talking about. So it's really nice for the operators because this is happening automatically. We're constantly monitoring the flow rate coming into the system. To illustrate this another way, this slide shows the control system. This is what the operator would see under typical flows. This is showing about an 80% of design flow. Note that there's freeboard available in the SPR tanks. That's this white space here in a few of these tanks. This is showing a 4-basin SPR system under typical flow rates. So because it's not reaching 100% design flow, under that fill cycle, there wasn't enough flow rate coming in quick enough to fill this tank here all the way to top water level. So there is actually freeboard available in a few of these tanks that isn't required to be used under design flow conditions or below. Note that only one tank is filling at a time, and that all of the flow is directed to that one tank. So this SPR tank 3 right here is in the fill process. It's only been filling for say 5 minutes, so that's why it's a very low water level. This tank will continue to fill and go through those steps that Brian talked about. It's in fill right now. It will enter react, go into settle, decant, and then idle. So you can see that these 4 SPR tanks are all working together in order to achieve each of those steps, and they're all at different time periods. This slide shows wet weather flow event of about 400% design flow. Now the controls have automatically adjusted to open all influent valves to use all of the tank volume available. So you can see here all of those influent valves are open for each of these SPRs, and that flow is being evenly distributed to all of the tanks available. Note that all of the tanks are operating at a higher sidewater depth now because you're using all of that tank volume that you have available. So if we go back to the average design flow, the 80%, you have that freeboard available, filling only one tank at a time. And then as the flows increase, the controls will automatically adjust, opening all of the influent valves at once and really using all of that tank volume that you have available. Note that you'll still gain tank volume in the form of freeboard. You'll still gain that back with each decant step because that is still happening intermittently. So this SPR tank 2 is in filled decant. So while it's filling and receiving flow and using that tank volume in order to help dissipate that flow rate, it is also decanting. So that this tank 2 here is still gaining freeboard back at this point. In summary, the OmniFlow Max technology provides the best of both worlds. You get biological nutrient removal during the true batch periods while you're under design flow conditions, and you also get better wet weather flow handling. This is easier for the operators because the control system automatically adjusts to the flow rates coming in. This control strategy can improve process control of existing SPRs. It can reduce the amount of tank volume required for new plants with high peaking factors because it would not require any influent equalization tanks or additional freeboard for the SPRs. So that's a cost savings up front for new plants as well. And it still provides that true batch conditions to achieve optimal effluent quality during average flows. So it really is the best of both worlds with biological nutrient removal and optimal wet weather flow management. Thank you very much. We'd like to open it up to any questions that anyone could have. If you remember the instructions that Beth gave at the beginning, you can chat us to send us any questions, and we will answer them as they come in.
I see a few questions in there, and Brian, I was just wondering if you're on mute right now.
Yes, we see the questions coming in. Thanks for the questions. So one question we have is, what improvements are required in order to upgrade or retrofit a conventional SPR system to the OmniFlow SPR Max? There's a couple things that we'll consider with retrofits. It's definitely an option to retrofit existing SPRs. So say you have an SPR that performs great under average flow, but it's just not very good at handling those wet weather flows. Because this is really a control change, it can be a very easy upgrade with just the control system upgrade. But another thing that we will want to verify is the hydraulics. So we'll want to make sure that the flow, the head loss between each SPR is equal, because once we open up each of the influent valves, we'll want to evenly distribute that influent to each of the tanks. So we'll want to make sure that either there's a a flow splitting mechanism, or that the head loss is about equal between all of the tanks. And that kind of ties into another question, asking how do you prevent short circuiting during wet weather flow rates while you're in those filled decant periods? And that's another design consideration that we would make upfront for a new system, but it's also something that you could retrofit. In order to prevent short circuiting, you really want to hydraulically separate the influent from the effluent. So typically we would be filling from one end of the tank and decanting from the other end of the tank. We're also typically filling at the bottom of the tank, and we would use our influent distribution manifold in order to fill under very low velocity conditions. So that has a couple benefits. It will help keep that influent velocity low, introduce it right into the sludge blanket so that that sludge blanket is not disturbed. But it also physically keeps the influent separate from the decant, so that sludge blanket is not disrupted during those filled decant periods. There's another question on the cost of retrofitting. So if the hydraulics and all of those considerations of separating the influent from the effluent, if all of the mechanical equipment is appropriate, then it's just a control system upgrade. So it's making sure that you have actuators on your influent valves so that those are automatically controlled, making sure that you have some form of flow measurement. So either a flow meter or monitoring the tank, the water depth in the tank, and then it's just a PLC controls upgrade. So if all the mechanical equipment is good, it's a pretty low cost just controls upgrade to get to the OmniFlow Max system.
All right, we've got several questions on effluent quality and how it's affected during the wet weather flows with the Max system. So in a traditional true batch system, this upgrade is particularly effective when you're seeing high peak flows that are above what you're designed to see at that plant, in which case the OmniFlow Max system will receive a better effluent quality, given that we're distributing that influent flow amongst all the basins rather than sending it all to one basin and really disturbing that sludge blanket and not getting a clear effluent. So by distributing it to, I'll say in our example, 4 basins, cutting that influent flow by 3/4. So you do see improved effluent quality.
There's a question on the freeboard that we talked about, specifically how do you gain freeboard back? And that both during the true batch mode that Brian talked about and under the storm flow events, the decanter is designed to pass a larger flow rate than the influent flow rate. So you're able to gain freeboard back by that mass balance of just decanting more quickly than the influent flow rate is coming in. And that's true with any SPR. We would do that with the true batch. The traditional system are also designed that way. And that's just to make sure that you can move water. The SPR does help act as a wide spot in the line, but we need to be able to get the water out more quickly than it's coming in. So the decanters are always sized in order to gain that freeboard back. There's a couple questions on if when the influent valves are called to open for this high flow scenario, what if your tank is in settle mode, or what happens with the decant valves under that scenario? So the control system, we kind of presented a very simple overview. It is a pretty complicated system, even with a traditional true batch SPR. So there's a lot of safety mechanisms built into the SPR, and the first one would be to never overflow a tank. So we're always monitoring the flow rate in the tank, and we have backup floats in the tank. So that influent valve won't open if the water level is too high. It'll wait until we can gain that freeboard back by decanting. And the other way to get water out is by opening up that decant valve. But again, there's a safety mechanism built in with that. The decant valve won't open unless it's completed some amount of settle, because we don't want to decant out those solids that are in the tank. It's got a bunch of backups built into the system that is pretty complicated on paper, but is very simple for the operators because it's all happening automatically in the PLC. Are there any other questions?
Looks like we had a question come in about filling through the ID manifold at the bottom of the tank, and if settling will be affected with higher TSS levels, and how do we prevent it? So I assume you're referring to during the max mode, where we're sending influent to all basins. And under that scenario, so we're sending less flow to each basin, and the ID manifolds are specifically designed to lower the exit velocity of that influent into the sludge blanket to a very, very slow velocity, and thus have minimal effect on disturbing that sludge blanket. So we're still able to get settling in the upper few feet of the tank, still get a fairly good clear effluent, and not have drastically increased TSS levels. And the decanter is always decanting from, say, 12 to 18 inches below the surface. So it's always at the top layer of the tank.
There's a question about handling any aeration, increased aeration demands under high flows. That's a really good question. Typically, these wet weather events are due to rainfall events. So we see that first flush has an increased load as those lines get flushed out by the higher velocity. But really, once that first flush is out, the pounds per day of BOD that we're seeing and needing to treat, we typically don't see that increase very much because of these storm flow events, because the bulk of that increased flow is relatively clean rainwater. So the aeration demand does not significantly increase, but that everything that Brian talked about with the true batch process and monitoring the dissolved oxygen levels in the tank and turning the blowers on and off, ramping up and down, that still applies to the max. So we're able to monitor and make sure that we meet those DOs.
Are there any other questions? All right, well, if there are no other questions, thanks to all the attendees for listening to our webinar. And have a good day.
Yes, and thanks to the presenters for sharing this information with us.